Having tools available to us that will help us make predictions about future populations or calculate population growth levels are extremely important. Today we'll be looking at uninhibited growth models. Our goals are to find functions that satisfy the equation dp dt is equal to k times p, and also solve application problems using exponential growth. Let's review what we've learned in algebra about exponential growth. An exponential growth model is a function of the form p of t is equal to p naught times e to the power of kt, where k is greater than 0. P naught, or p sub 0, is the population at time 0. P of t is the population at time t, and k is the exponential growth rate for the situation. Doubling time is the amount of time necessary for the population to double in size. As you can see from the graph on the right, as time progresses, p of t increases dramatically. This is called exponential growth. I'd like to take a look at the website intmath.com for a dynamic example of exponential population growth. Let's take a look at today. According to this model, the world population is approaching 6.8 billion. On the lower left, we can see the rate of increase is approximately 1.31% per year. Remember, rate of increase is related to the derivative. Derivative represents a rate of change, which can be a rate of increase as well. So this actually represents the derivative at this instant in time. Down below, it's kind of interesting to note, it tells you how many people per second are being added to the world, how many people per day, and how many people per year. On the upper right, you can click on choose a year. Most of you were probably born in the 80s or 90s. You can see in 1980 we were looking at about 4.9 billion. 1990, 5.7 billion. And as time passes, you can see the population starts to grow dramatically. And in fact, it gets quite scary as we reach the year 2100 and even 2200. Now, of course, this is just a model, and like any model, over time it could break down. There may be questions about whether the world could even support close to 50 billion people. Is there enough water, air, food, and so on? That would be quite a philosophical discussion. Let's go ahead and go back to our presentation and take a look at the relationship between exponential functions and calculus. Remember that a derivative represents a rate of change. A function y equals f of x satisfies the equation dy dx is equal to k times y, or it can be written f prime of x is equal to k times the function f of x. If and only if y equals c times e to the power of kt, or f of x is equal to c times e to the power of kt. So really what that's saying here, the important part, is that if you have the derivative and it's equal to a constant k times the original function, this value of k will be your exponential growth rate, or the value of k. That's true only when you have the exponential function. And just to kind of refresh your memory about this connection, it may seem foreign, but in fact, earlier in the semester when we were studying the derivatives of exponential functions, for example, if we had f of x is equal to e to the power of 5x, then from your derivative formula, you know the derivative would be equal to e to the u times u prime, where 5x would be our u. So we would have e to the 5x times 5, or 5 times e to the 5x. Again, the connection here is that if we were given this derivative and we knew this was our constant k, it would give us the growth rate in our exponential function here, 5. Another way of stating the same relationship that deals specifically with population growth would be this. dp dt is equal to k times p, or p prime of t is equal to k times p of t. Again, if we have the derivative of p with respect to t, and it happens to be equal to a constant times the original function, this value of k gives us our exponential growth rate. And looking below here, it doesn't matter whether we use p sub 0 or c for the initial population. Let's go ahead and take a look at an example. Suppose that an amount p sub 0 in dollars is invested in a savings account where the interest is compounded continuously at 7%. Well, if that's true, if it's compounded continuously at 7% per year, then we can conclude that the derivative of p with respect to t would be 0.07 times our function p. The continuous interest rate would be our value of k. Let's look at this in more detail. We know the continuous interest formula from algebra is a equals p times e to the power of rt. Well, the formula that we just referred to is just a slight variation of this. Essentially, we're using p of t instead of a, we're using p sub 0 instead of p, and we're using k instead of r. So in this case, what we know that if this is given, that our k, or our growth rate, must be 0.07. Therefore, our function p of t is equal to p sub 0 times e to the power of 0.07 t. Suppose you invest $100. What is the balance after 1 year? Well, if we invest $100, that would be p sub 0, and t would be equal 1 year. We need to find p of 1, which is equal to 100 times e to the power of 0.07 times 1. Let's go ahead and calculate this. 100. If we hit second natural log, it'll bring up e, and we can just type in our exponent. Times 1 is not needed, but I'll put it in there. And it looks like we have $107.25. Let's take a look at one more question for this situation. In what period of time will an investment of $100 double itself? Here's our function. So if we start with $100 and double it, we would have $200. Our initial investment is still $100. Okay, so to solve this exponential equation, we need to isolate the exponential part. Divide by 100. So we'd have 2 equal to e power of 0.07 t. Now if we take the natural log of both sides of this equation, we can apply the power property and rewrite this as natural log 2 is equal to 0.07 t times natural log e. Remember, natural log e is equal to 1, so it simplifies to this. Now I want to pause here for a moment and just make a note here that in order for something to double, notice that algebraically we end up with natural log 2 is equal to, this would actually be k times t. It's just in this case we do know the value of k. This idea will come up momentarily. Okay, to finish this problem we simply need to divide by the coefficient. So if we divide both sides by 0.07, we'll get t approximately 9.9 years in order for this investment to double. Let's take a look at a shortcut formula to find doubling time. The growth rate k and the doubling time t are related as follows. As I mentioned in the previous example, k times t is equal to natural log 2. Now they're using a capital T here just to denote that this time is the doubling time. So notice how if I want to find the growth rate, I can simply divide natural log 2 by the doubling time. If I want to find the doubling time, we can just divide natural log 2 by k. Now in most cases I like to use the exponential equation formula and set it up and solve like we did in the previous example, but sometimes these shortcuts can be handy. Let's take a look.